Okay, thank you very much.
You are now muted.
I wish I were in such a beautiful place, but anyway, I'm very happy to be here and can share some mathematics with you. I will talk about this work, which is a joint work with Arman Arévalo and Edgardo Roldán Pensado. It is a zero-sum bounded discrepancy zero-sum squares in bounded discrepancy matrices with values in -1 or 1. And let me see, I divided the talk into 3 parts. So first I want to talk a little bit about the story of this project, and therefore I will talk about a problem called the Erickson matrices problem, which can be seen as a prototype or typical canonical problem in Ramsey theorem. Then I will take a few minutes to talk about some variants of Ramsey theory, variants that I really liked, that I think are interesting and in which I have worked in recent years. I want to emphasize in this part the similitudes, the difference and similitudes between the theories, and which is like the main philosophy in each one. After that, I will come back to the concrete, the particular problem that we attacked, and present the result that we prove in this particular context that I will explain later. So let's start with the Erickson matrices problem. I will give just these 2 definitions. So think of binary square matrices with entries in 1 and 0. And then in such a matrix, a square is a 2 times 2 submatrix of this form. For example, here you have a square, and we are going to be interested in we want to look for constant squares, which are squares with all entries the same, with the same value. So this is a square, but this is not constant. Here you have another square, which is also non-constant. So an Erickson matrix is going to be a square binary matrix that contains no constant squares. Here you have as a constant square. Therefore, this matrix is not an Erickson matrix, and we want to study Erickson matrices. So once we have a definition, we want to see an example of an Erickson matrix. I can give you this small example. You can check in this 3 times 3 matrix that all squares are non-constant. Therefore, this is an Erickson matrix. And the Erickson matrices problem is actually the following question: how large can an Erickson matrix be? This problem was posed by Martin Erickson in 1996 6 in his book, Introduction to Combinatorics. And I learned from this problem some years ago in a conference in Seville. I learned from this in a session problem from Shalom Eliahou, and I found the problem very interesting. I will tell you the answer to this question, the solution of the problem, and then I will talk about the variant that we are going to consider. So here you have another example of a larger Erickson matrix, which is not as trivial as the previous one. This is 8 times 8. And if you know a little bit about Ramsey theory, maybe you should recognize this problem as a Ramsey type problem. And if you know a little bit more, maybe you can recognize that the answer to this question is not arbitrarily large. So we cannot have Erickson matrices arbitrarily large. This follows by a classical theorem in the domain of Ramsey theory, a theorem by Galai. But anyway, Erickson himself knew that Erickson matrices couldn't be arbitrarily large, and actually he proposed as an exercise in the book to prove this huge upper bound for the size of an Erickson matrix. That is, we cannot have an Erickson matrix larger than this huge upper bound. So the question is how to find the precise value or to improve this upper bound. But now let me change the language to the to the coloring language, which is the Ramsey theory language, and look that a binary matrix can be seen as a two coloring of a grid. So in Ramsey theory, we have some mathematical universe, and then we consider all colorings of this universe, and we ask for the existence of monochromatic substructures, provided that the universe is large enough. So this problem fits in this context. So instead of thinking of binary matrices, we are going to think in two colorings of this grid. Or if you want, you can think on the lattice of points in the plane with positive integers entries. And of course, a square is going to be a square, the same object, and to be constant is exactly to be monochromatic. So rephrasing the Erickson matrix problem, what we are doing is what Erickson asked is exactly to determine the minimum positive integers that we are going to denote like this, such that every two coloring of the grid or the lattice, which is large enough meaning that the length is greater or equal than the parameter that we are going to study or that we are looking for, contains a monochromatic square. So this is a typical Ramsey type parameter. Those parameters are in general hard to determine. And in this context, in 1908, the best lower and upper bound for the value were by Maria Axenovich and Manske, 13 on one side, and this again huge upper bound, which was in terms of the van der Waals number for two colors and arithmetic progressions of length 8. This value is still unknown, but best upper bound is again huge. It was better than the exercise proposed by Erickson, but anyway, it was quite large. So after 2 years after this work, this is a beautiful paper. Here I have a picture of the paper, actually. Let me show you. Here is an example of an Erickson matrix or a two-coloring of the grid, as you want to see it. So you can check in this picture that there are no constant squares. This is a 12 by 12 arrangement, therefore proving this lower bound. And well, I was saying 2 years after this, Shalom Eliahou and Bacher proved that it was actually a surprise that the value, the exact value for this parameter is 15. So they were able to show the exact value. They use some computational assistance, but together with very clever arguments, and they do a case analysis looking for a specific shapes of the coloring or the matrix. Anyway, the solution is 15. The precise value for this parameter is 15. So I learned from this. I found this very nice, beautiful problem, and I thought, okay, maybe I can study some of the same problem in some of the variants of Ramsey theory that I used to work on. First one, so this is like in a big context in Ramsey theory. So we have a mathematical universe, as I told you. We are going to consider all colorings. The number of colors can be greater than 2. And then we are going to choose some substructure in the universe that we want to prove that it's inevitable to find this structure monochromatic, provided that the universe is large enough. Remember that a coloring, which is just a mapping from the universe to a set of colors, can be also viewed as a partition of the universe. This can be, as in our case, a lattice or a grid, or can be the set of integers or the set of edges in a graph. There are many different universes that we can consider here. So a coloring is a partition. These parts are called the color classes, and a monochromatic set is a set which is inside one of the color classes, And the first variant that I am interested in is called anti-Ramsey theory, or also sometimes called rainbow-Ramsey theory, where instead of monochromatic sets, we are interested in studying rainbow subsets. Rainbow, meaning that the object that we want to find, we want to know if it's transversal to the coloring, in the sense that each of its elements belongs to a different color class, and we cover all color classes. So all colors difference in my object. I want to study if, as monochromatic structures, rainbow structures are also inevitable. But in this case, of course, we need to take into account somehow the density of the color classes. We cannot expect to have rainbow structures if, for example, we have a color class which is empty. But actually, it's in general, usually we need all color classes to be large enough. Not only the universe, but the color classes, all of them need to be large enough in order to warranty the existence of these rainbow subsets. There is another variant, which is the one that I'm going to talk more in this talk, which is called the zero-sum Ramsey theory. There, instead of monochromatic or rainbow structures, we are going to be interested in studying the existence of zero-sum subsets. Of course, here we need to provide the set of colors with some additive structures, which means either the set of colors is a group where we can add the colors, or is a subset of a group. In this part of the theory, the most common or the most studied part is to consider the set of colors as a cyclic group, or some group with some torsion. And there is the whole theory that started with the Erdos, Greensburg, and Sieve theorem, the Davenport constant, etc. But when the group of the colors has no torsion, then we have a similar or analogous problem as in the anti-Ramsey theory. We cannot expect to have results or to force the existence of zero-sum subsets when the group has no torsion, unless we require the coloring or the color classes to be large enough, each of them. So in this sense, the theories, they have some similitudes. So to consider here, for example, a set of integers is not so, it's not so well studied as the other cases where the colors are elements of a group with torsion. So in particular, in a very particular case, I was interested in studying colorings where the colors are just the set, a set of two integers, -1 and 1. As I told you, to force the existence of a zero-sum subset, I need to take into account the discrepancy of the whole coloring, which is the deviation of the whole coloring, just the absolute value of the sum of the values of the coloring along the whole universe. So it's the difference between the -1 or 1, or how close in cardinality are the color classes. So if I have some controller on this measure, then maybe I can imply the existence of a zero-sum structure. In particular, so this is a context in general about the problems that one can study or one can consider. In particular, for example, a very natural question is the following. Consider as your own universe just the set of integers. So you think of a long sequence of pluses and minus, and if the discrepancy is small, you can control somehow the discrepancy there. Then can we ensure the existence, for instance, of a zero-sum arithmetic progression? The answer to this question is yes, we can do it. And this is a consequence of I just want to mention, of a work with my colleagues Jair Caro and Adriana Hansberg, where we study not the whole set of arithmetic progressions. We study just K blocks, which are arithmetic progressions with difference 1. In this case, in this particular case, where the difference of the progression is 1, I wanted to show you this theorem because we studied not only zero-sum blocks, the existence of zero-sum blocks, but we can measure, we can choose 3 integers, t, k, and q. K is going to be the length of the block or the progression. T and Q are going to measure how small the block, the discrepancy of the block I wanted to find. And Q measures the discrepancy of the whole universe. So we have all parameters in the hand, and we can tell how large the universe should be in terms of these 3 parameters in order to force the existence of the small discrepancy object that in this case is a K block. This bound is tight, and we also provide in this paper the description of the extremal sequences. So I think it should be really interesting to make some, maybe challenging, to make some analogous study for arithmetic progressions or other structures in between blocks and arithmetic progressions, or at least to bound the Ramsey type parameter here, or zero-sum Ramsey type parameter here, should be interesting. So those are the kind of problems that I'm interested in. And in coming back to the case of matrices or plain lattices or grids, and studying the existence of zero-sum squares, now it's clear what the problem is. Our universe is now this grid, and we want to know that if this is sufficiently large and the discrepancy is small enough, we want to know that if under these conditions we can ensure the existence of a zero-sum square. This is an analogous of the Erickson problem in the context of zero-sum squares with this range. So let me see. So we start this project with Alma and Edgardo. I'm sorry, I want to go back. And so first of all, we needed to have an intuition of how bounded the discrepancy should be in order to imply these zero-sum squares. And we start exploring examples. For example, these examples that you have in the screen, it can be generalizes, and the discrepancy of it is roughly n squared over 2. So maybe we need to, so this indicates us that we need to go linear in the discrepancy in terms of the length of the grid. But there are other examples that came out quickly, and we need to take into account all these triangular arrangements or matrices. If you look at them, they are zero-sum square free. There are no zero-sum squares in them, and we can measure the discrepancy very easy in these matrices. And the smallest one is the one that is almost, through the main diagonal, and the discrepancy of this example is precisely n. So we need to take this into account. So at the first moment of the project, we start exploring by computing assistant several examples in order to see if we could found some pattern or see something about the existence of these zero-sum squares. Here you have more zero-sum square-free matrices. At this point, I was not very positive with the project because we didn't see nothing very clear here. But after, we keep exploring those small examples, and then we could observe something interesting. Actually, for lengths between 5 and 11, we observe that all matrices with a small discrepancy, small meaning less or equal to n, contains a zero-sum square, except for the triangular example that I show you. So at this moment, we thought, this could be a conjecture. Actually, maybe we can try to prove that. Actually, for any length greater or equal than 5, and this bound in the discrepancy, we can ensure a zero-sum square, except, as I told you, for the triangular case. And yes, actually, that was what we were able to prove. We were able to prove that the existence of the zero-sum squares in these -1 colorings of the grid is forced, provided that the n is large enough, which large enough is just, in this case, just 5, and with only one example, which is the triangular case here. And the bound on the discrepancy that we work with here was, as I told you, n, the length of the grid. So the main idea, we proceed by induction. So I want to give you just an idea of how the proof goes. We start with a big zero-sum square-free matrix with a small discrepancy, and we split it in 4 submatrices. And then, as we know that the discrepancy is small, we are able to manage with an interpolation argument. We can prove that there is a large enough submatrix inside, which is triangular. And then after we find the relatively large triangular matrix, we can make a case, we can spread the information. So to have a large triangular matrix implies or compromise or forces a lot of the values close, and then we can still spread this information in order to force the discrepancy to be larger that it should be, and then prove the theorem. But as to make our induction works, we needed to consider not only squares matrices, but squares and almost squares matrices. So what we actually prove is this theorem, which is a little bit stronger, where we consider these matrices which are almost square, and in order to make the induction argument to work. So next, to end with, I want to mention just some open problems. Of course, we can consider different problems in this context. We can consider other ranges. I mean, we can still studying the square problem in the zero-sum context, but instead of consider the set of colors -1 and 1, we can consider the most classical coloring, which is by using the elements of a cyclic group, for example. And another direction is to look to study other shapes, somehow in the line of the Gallais theorem in Ramsey theory. Also, we can think on increasing the dimension, and I mean, there are many options in these variants, but I want to present or to finish with a particular conjecture that we propose concerning the specific case of the squares in the planar lattice, and with the range of -1, 1, which is the one that we are that we study in this work. So what we observe in our computational exploration of smaller cases is that actually for these cases, we can obtain the same result, not only for the discrepancy bounded by n, but by 2n. So with a little bit, well, with more effort, maybe we can improve our theorem, but moreover, we are convinced that actually for every positive constant, we can, as in the work from about the block that I showed you, we can measure the discrepancy with a parameter that we can choose, which in this case is C. And then if the discrepancy of a matrix is upper bounded by C times n, n being the side of the matrix or the grid, then we can find an n, which is like the parameter that how large should be the size in order to force the existence of these zero-sum squares. Again, we need to exclude the triangular case that we cannot do anything with it in. And so thank you very much. This is all.